All right. So you're probably a little upset today because we're not doing any math. So we're gonna end the school year of new material without any math. So on a sad note, no math today. What we're going to talk about today is called the kinetic molecular theory. And it has a lot to do with how we measure temperature. Okay, but again, we're still basing it off gases. And so throughout this discussion of the kinetic molecular theory, we're going to be using this little model over here on this picture to kind of help explain to us what happens to gas molecules when environmental conditions change. Okay. Now we hear the word kinetic. What does that mean? What does kinetic mean? Moving, there we go. Yes, it's the movement of particles. And so we're going to see just what, kind of some of the things that alter a gas's behavior based on their movement. So we've got some main tenets, meaning main pillars of the kinetic molecular theory. First one is that gases consist of large numbers of molecules that are in continuous yet random motion. They cannot direct the direction in which they are moving. Another statement of the theory says that the combined volume of all the molecules of a gas is negligible relative to the total volume in which the gas is contained. So that notion allows us to make the assumption or make the point that most of the volume in a gas is simply empty space, which allows for us to compress gases. And oftentimes we can compress gases to the point where they actually are close enough that they reform liquids. Not necessarily the state they prefer to be in, but we can still do it. Within a gas, attractive and repulsive forces between gases the molecules are negligible, again, because of that large distance between the molecules themselves. They don't have a whole lot of interactions. Now, energy. Now, this is something that we're not going to be able to get into this year, talking about calculating speed of certain molecules. But the molecules themselves can transfer energy during collisions, much like if you're playing pool, the pool balls can transfer their energy to the other balls around them. Okay, but the average kinetic energy does not change with time, as long as the temperature of the gas remains constant. So with that statement right there, when we say the average kinetic energy, that, when we measure temperature, is what we are measuring. The average energy associated with the molecules of what we're measuring, as long as temperature remains constant. So the average kinetic energy is proportional to the absolute temperature. Therefore, temperature plays the most important role in this kinetic molecular theory. So watch this a little bit. A couple of them.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly. Little warning.
So what's happening inside that tank is, as we are adding heat energy from the fire, it's speeding up those molecules, okay? In areas where, as I said, where that liquid is not present, the vapor pressure, because of the increased energy being given to those vapor molecules in there, they're speeding up. And when they start speeding up, they start creating more collisions, not only with themselves, but between the molecules and the container itself. And so as the heat is starting to soften the material of the tank, those vapor molecules are hitting that side of the tank much more often and much more vigorously, with much more momentum. And so eventually, as you see at the very end, the vapor pressure builds up so hard, so high, that the weakened structure can no longer contain it. And you see what happens. So temperature is, as they say, it's just a demonstration of it being one of the most important parts of this kinetic molecular theory. So now let's put some of those notions of this theory into practice here, okay? So we have a sample of O2 gas. It's at STP, or standard temperature and pressure, initially, okay? We take that O2 gas and then compress it to a smaller volume at constant temperature. There's a key few words right there. We need to figure out what effect does the compression of this gas at constant temperature affect on the average kinetic energy of the molecules. So do you think by compressing it while maintaining constant temperature, do you think it'll have any effect? And if so, what effect do you think? And what's maintaining constant? What's staying the same? Temperature, okay? So if we're not changing the temperature and simply reducing the volume, is that going to speed up the molecules at all? No, okay? We're not adding energy to the system, so that's not going to change. What about the average speed? Well, if their kinetic energy is not changing, do you think their speed's going to change? Nope, it's not going to change either. Now, what about the number of collisions they're going to make with the container walls in a given amount of time? Imagine if I took all of you and said, all of you could only stay in this area of the classroom, but you have to be moving constantly. Do you think that you're going to be hitting the sides of the walls more frequently than if you were spread out and allowed to travel? Absolutely. By reducing the volume, you've reduced the area that they can move. And again, their movement is random. So you're going to have an increase in the amount of times that you're going to hit the wall. Now, what if I said, okay, in this little square right here in the front corner of the room. That's the only space you have to move around randomly. And what if I said this door, this specific location? Do you think you'd have an increase in the number of times that the gas molecules collided with that door? Absolutely. Again, compare it to this open room, and you're just wildly roaming the room. Okay. If you just have this whole open room, the number of times you're going to hit this specific location is going to be significantly less than if you only have this little square to move around. Okay. But what if we're talking about speed in this new situation? Okay. RMS speed just stands for root mean square speed. It's really just a measure of the number of molecules that are moving at a particular speed. So we've got N2 molecules in a gas sample, okay? What's going to happen to the speed of these molecules if we increase the temperature? What's going to happen? Is the speed going to remain constant? Is it going to decrease, or is it going to increase? Why is it going to increase? They're moving more because we did what? We heated it up. We added energy to them. So we're going to increase the speed because when you heat them up, you increase the kinetic energy. Thereby, you're also increasing the speed at which the molecules are traveling. So that first answer is increase. What about if we increase the volume? Again, this is a completely different situation, okay? Is increasing the volume going to change the speed of a molecule? Or is it going to remain the same? What do you think? We simply just increase the volume. Ask yourselves, are we adding any energy when we increase the volume? No. So, without the added energy, the molecules just go about their business. They're just going to have a lot more room to do it in. So the speed of the molecules is not going to be affected by an increase in volume. And lastly, what about mixing the sample of argon at the same temperature? If we place argon molecules into the nitrogen gas, but also maintaining temperature, is it going to increase, decrease, or remain constant the speed of those molecules? What do we think? Anytime we're talking about this, ask yourselves, are we adding energy? We simply just add molecules, are we adding energy? No. And it says we're maintaining temperature. So again, just simply adding molecules will have zero effect on the speed of the molecules. And that is the essence of kinetic molecular theory. Everything is driven by energy. That energy comes from the temperature, whether being decreased, increased, or remaining constant, going to have the most effect on the movement of the molecules. And like I said, it was going to be a short discussion today. And with that, we are done. All right. Told you. Simple, 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 simple today. All right. Let me stop recording. Now,